Yeah. Well, ladies and gentlemen, I'm the chairman and the speaker. So I just introduced myself, Peter Rowlands, from the University of Liverpool. So I'm going to talk about the inside the Dirac equation. Let me just call the share screen. Now, the way I'm doing this talk is totally different to the way I used to do them. I used to come up with my ideas and explain why they work for this and that and the other. But I found that's a bad strategy. It's much better to start with something that's known and accepted and show how, by pulling this out the right way, you can get to the right ideas. So I'm going to try that this time. This is a bit experimental because this is a huge file and I'm not going to get through all of it. But this is a preparation for a paper I'm hoping to submit to a particular journal. Though we'll do something for AMPA as well. What do I press to keep it going? Do I have to
arrow?
Doesn't work.
On the keyboard.
I know, I've tried it on the keyboard. Okay, we'll start with the three most famous quantum mechanical equations, the Schrödinger, Klein-Gordon, and Dirac. And we're using the convention h bar equals c equals 1 all the way through this talk. So those are the three equations, and these are what people have used for quantum mechanics. That works. Now, the first two of those equations, we can start with something that looks classical and change it over by using the standard operator formalisms that we can do for those. So in the first case, we use the E minus V equals P squared over 2m. And from the Klein-Gordon, we use E squared minus M squared equals P squared because we introduce relativity as well. And it's important to show that the Klein-Gordon will reduce to the non-relativistic when M is very large. And the thing is that never ever is E squared minus P squared equals M squared not correct. It's always correct. It's just that we don't notice it if M is huge. Now, the Dirac equation is different from those. It's plucked out of the air. You can't take a classical equation in the ordinary way and introduce abstract mathematical concepts. You can't do that. But what you can do is introduce new concepts, and Dirac introduced these terms alpha and beta from nowhere. But the purpose of that was to reduce a squared equation in squares, into an equation in non-squares, a linear equation. And it seems rather ad hoc. It works, but it's just to introduce anti-commutativity so you can get rid of the unwanted cross terms when you square it. However, I don't think that's the right way to look at it. Alpha and beta are actually incredibly significant introductions to quantum physics. We've not really got to the bottom of them yet because we haven't really understood everything about them. They're not just mathematical operators for a convenience. There's something more than that. We'll show them there's plenty of significant meaning. So Dirac equation, it uniquely applies to fermions. No other equation only applies to fermions. And these are the most fundamental physical systems, so it's a special equation in many ways. And this forcing us into using this abstract mathematics forces us to confront nature in a way that we've never confronted nature before. We're simply forced into it by mathematical considerations. And now Dirac managed to get some immediate physical meaning out of alpha and beta. He realized that they could be represented by 4x4 matrices with just ones and zeros and stuff like that in, and found immediately that there were 4 simultaneous solutions for a single particle. And he said these could represent particle and antiparticle, spin up and spin down, or left and right-handed. And this is quite extraordinary because your solution has to include an antiparticle as well as a particle. And this is something new. However, these matrix representations aren't in any way unique, and there are lots of alternative formulations. One particular one is called the covariant form. And the reason is that in the original equation, it's not covariant because you don't have, the gammas are not, sorry, the alphas and betas are not just on the dt and dx. However, in the covariant form, we replace beta with gamma naught, a new concept, and it's the same thing, but we'll give it a new name. And we make beta times alpha a new component, gamma, with 3 components. And we multiply all the terms by gamma in a 0 in advance, so we get the equation on the left and the abbreviated form in the next bracket equals 0. And the 4 terms are mutually anti-commutative 4x4 matrices. They square respectively to the identity, minus identity, minus identity, minus identity. And there's a 5th anti-commutative matrix which doesn't appear in the equation, which is also square root of the identity, defined as I gamma naught, gamma 1, gamma 2, gamma 3. Now, if we multiply the gammas together in every way, we do tensor product, we get 64 terms, and that's what it looks like. And so we now know that this gammas are not just 4 objects, they're part of something bigger, a group of order 64. And one of the significant representations of these gammas is to use Pauli matrices, which are the sigmas in the brackets for the gammas. And the Pauli matrices are isomorphic to multivariate vectors. That is, vectors, these are an important Clifford algebra, and here I've got Clifford's works with me, complete papers, and they're an important Clifford algebra. Clifford, the infinite number of Clifford algebras, they're the basic Clifford algebra in which you've got complexified quaternions. And these complexified quaternions have the properties of vectors, except that they're more than vectors because they have a full product instead of just a scale and a vector product. The full product is a combination of the two. But in fact, all vectors are multivariate vectors. It's just that we didn't realize it before. It's only how we use them. And if we use an electromagnetic theory, we can make Maxwell's equations one equation. And if we use them in the Schrödinger equation, we can generate half spin without having an external input, which we can't normally do. So these have got some extra value and meaning. And as I've said before, the 3 multivariate units, RJK, are I times the corresponding quaternions. Quaternions being square roots of -1, which are dimensional. And pseudovectors are vectors multiplied by I, and they're actually quaternions. Pseudovectors are the same as quaternions. And pseudoscalars are scalars multiplied by I. Now, how do you construct a Clifford algebra? Very easy. You just take any number of quaternion sets you want, as long as they're independent and commute with each other. It doesn't matter how many you do, that's a Clifford algebra. And you can also complexify the whole thing, and that's also a Clifford algebra. And they form groups with orders based on 2. So quaternions are order 8, they're a basic Clifford algebra. Complexified quaternions 16, double quaternions 32, and complexified double quaternions of order 64. So lots of people, even Dirac himself, said the Dirac algebra is equivalent to a Clifford algebra. And they just said that and they've done nothing about it. Or if they've done something about it, they haven't done enough. If they're order of 64 and they're Clifford algebra, then there's only 3 algebras that fit that are Clifford algebras. They can be a double quaternion, so quaternion multiplied by another quaternion all the way through, tensor product, a vector quaternion, a multivariate vector multiplied by a quaternion, or a double vector. And it doesn't matter which of those we choose, we get the same results. But one thing about the double vector is it suggests that there are 2, that if this is a very fundamental equation, this is very fundamental mathematics, it's like having 2 spaces, 2 full vectors. One of the ways you can derive them is by using 2 sets of Pauli matrices, which I said are isomorphic to vectors. So once you recognize this, the whole matrix structures are an option. We don't have to use Dirac's matrices or anybody else's version of them. They're useful in many ways, but they're not as useful as other methods of doing it. We can use algebraic symbols and at any time convert them to vectors if we choose. We get much more manipulability if we do that. Now with Sydney, I've done a paper in which we do 8 equivalent ways of generating the algebra. And we've mentioned the first 3 already. And then you can have all the products of gamma to gamma 5. You can have all the products to gamma 3, and then just use I instead of gamma 5. You can have the products of beta and alpha and I, and 2 sets of polar matrices. I mentioned that one. And you can have the full set of 4x4 matrices. And we've done all of those, worked them all out, all 64 terms, and shown how they match each other totally. But the first 2 are particularly interesting because these suggest physical meaning. These aren't just a mathematical operation, there's physical meaning to this. And that's how we get a vector quaternion algebra. The reds are a set of quaternions, and the blues are a set of vectors. And we've also got complex I in black there. Now, what I want you to notice there is that we've got 6 on one side and the minuses on the other side. We've got 6 objects. Now, these objects here, and say take the top row, these objects could be slotted into the 5 positions in the Dirac algebra. The ones for, in order, momentum, energy, the first 3 for momentum, the second one for energy, the third one for mass. Or if you like, d by dt, and del and the mass term. And what's more, those 5 will be a set of generators for the group. If you just take those, you can get the whole group. So those 5 just tell you what the group is. In the first few places, you might need to multiply by complex I, but that's already part of the structure anyway. And again, this is using 2 sets of vectors, a red one and a blue one. And it's exactly the same structure. So this has clearly definite physical significance, which the gamma algebra, as it's used, doesn't have. It's just an algebra. A pentad, that's 5 objects. We need a pentad to generate the algebra. So we don't normally see all 64 terms. But there's 2 aspects to this that are important. One is that all the terms are important, even though we don't see them all in the equation, because they are part of the algebra. And the second is that all we need to do relativistic quantum physics is a dual space. There's no other source of information. And one space, the blue one, is what we normally call space. The other one's made up of everything else. If you put a quaternion and a complex number together, you get a vector. So that would be equivalent to another space. But it doesn't manifest itself as a space because the different units are not part of the same physical thing. And if you put these 2 physical spaces together, the singularity that we call the fermion exists on the boundary of these 2 spaces. That's what we're doing. And we can also see how the symmetry is going to be broken. If I take, this is from the double vector representation. If I take those 5 in that first row of things, you can see that the I, J, and K, the red ones, are attached to totally different objects. The middle 3 are attached to a vector, and the outer ones are attached to, the K isn't attached to anything, and the J isn't attached to anything, but the middle one is attached to a vector, and we've broken the symmetry. And one of the things that I'm saying here is that we got 5 units is less than 6 units, so that's better in that sense, but it's not symmetrical. 6 units you could generate the algebra with the 6 units and it'd be beautifully symmetrical. Generate it at 5 units, which is less, and it won't be symmetrical. It'll be broken. The result will be symmetrical, but the starting point won't be. So I'm going to do my vector quaternions, and I'm going to take, I've got a complex number, I've got a vector, I've got a unit, just a scalar unit, and then I've got a quaternion. And I'm going to spread that quaternion out onto the 3 other things. And you get one goes on the I, that's K, one goes on the this is just arbitrary which one you choose, but this is the ones I've chosen in the past. One goes on the vector, that's the I, and one goes on the the unit, scalar, that's J. So you can see we've got two spaces, the one made up of the complex and the quaternion, which is the red one, which is broken, the other one which isn't, which is our space. And now we can match the 5 generators to the 5 gamma matrices in lots of ways. I could choose that one, I could choose any of those two and stick those in the equation and it would be hunky-dory. But always one symmetry is broken and the other is preserved. And because you've got dual space, we've got meaning for a lot of things that we wouldn't otherwise have. Spin half, because it's in 2 spaces at once. Berry phase. Zitterbewegung, switching between the two. Vacuum, what's vacuum? That's the other space, isn't it? And lots of other things. And we're getting the first inkling of what the standard model is about because we've got 5 asymmetric generators. And we haven't done anything other than manipulate the Dirac equation. We haven't got anything new physics in here. It's just pure mathematics. Now, people have argued that we've got a formalism which works because they do equations and they do Dirac equation, they get answers. But they don't get very many answers for it. It doesn't work very well. It doesn't give us the standard model at all. There's no explanation for their mathematical structure. You've got a whole apparatus of stuff we don't really need. Spinors, primitive and idempotent minimum left ideals. Not at all necessary. There's no symmetry in the existing formalism. It's a horrible mess. And there's a lot of redundancy. And even you've got a free particle, the simplest solution you could possibly imagine, a free particle. And you try to actually do the Dirac solution for that. You don't get one equation, you don't get one idea, you get 4. You get 4 wave functions and you get 4, it's just impossible to do. And you also mix up E and M and P, PX and IPY. No counterpart in nature to those. So the gamma matrices, when you actually do them and put them down as matrices and see how the equation works out, you just get a big fragmentation. You mix up energy, momentum, and mass. It takes up a huge amount of space. You need 64 units to do it because you've got 16 times 4 spaces. 16 for the operator and 4 for the wave function. And there are 5 terms in the equation, and we got 5 in the algebra, but only 4 have a gamma matrix. Yet there's 5 in the algebra. So what are we going to do? Well, we have to defragment. I used to get this from how we used to do disks. You know, they defragment the disk, and you sort of defragment, and you get it all this horrible jumble, but would become nicely arranged, simple colors. And those are our bins: energy, momentum, mass. We've got to put them in different bins. So let's first of all start by using a set of these algebraic operators, and any set we choose out of many of these will work. But it's important that they all work because they all mean something. And if we choose the first mapping, that's what we get. But now let's do something that people don't, make a fuss about. I'm going to multiply that by J from the left. It's absolutely trivial, but it leads to profound consequences. That's what you get. And now we've got 3 bins which separate out our energy, momentum, mass. That's nice. That's what we would like. But what happens when we try a plane wave solution? So plane wave is up there. It's a dead easy differentiation. We get that object there, the Ke, etc. And I can abbreviate that by collecting the momentum terms together. And P is always multivariate. But this is only valid. You can't get 0 from the exponential term. That will never 0. That term will never be 0. You can only get 0 if you multiply that E, that Ke term, by something which zeros it. And the only thing that will 0 it is itself, or a multiple of it. So we found something out about the wave function we're using. It's a nilpotent. It's a square root of 0. It's also completely explicit. There's no black box. There's no size. We got rid of all that. You know exactly what it looks like. And this must have always been true because we multiply from the left. So it must have always been true before we even multiplied it. And we can now import back what we learned from Dirac himself, that there are 4 solutions. So this is fermi and antiferm, plus and minus E, obvious. Spin up, spin down, plus and minus P. And these are both amplitude and phase. So we can now represent our 4 components. Right, this is the 4 components of psi1 and psi2 to psi4. And each of these will be operated on by that operator. And you notice that the 4 phases, the E to the I terms are all different. And the 4 sort of amplitude terms, these are all different as well. But the operator is the same. Now we're going to do something that's going to change that. Too many spaces forward. To get on. Just a minute, I've got to go. Well, miles past it, haven't I? Hold on. This is escape and do it again. Share the screen again. I don't know how we ended up at the latter half of it. Right, let's do that. It's still not helped us, but I can scroll up and go back to somewhere. I'm certainly not going to get through all of this, so don't worry. I've done that. Let's slideshow from current slide. It's very temperamental, this machine. It tells you off if you do something wrong and how. So we got there. Now, what we're going to do, we got that form of the equation, the gammas, by multiplying from the left by gamma 0. So why not do the ultimate and multiply by gamma 5? So we're now actually doing that. That's what the J was. We're multiplying it by gamma 5. And this is the covariant nilpotent form. It's covariant and it's nilpotent. It squares to 0. It changes the gamma 0 and the gamma, but that doesn't matter. It just changes to a different form, a different matrix, but there's still gamma 0 and gamma. But it's not the only transformation we can do. If you have got 4 different phases, you've got no hope of getting an easy solution. You need one phase, because that's the thing you have to guess to solve this equation. You've got to guess what the phase might be. And once you guess the phase, everything else flows. So if you remove the 4x4 matrices, we can actually linearize it, but it also gives us more logical space because we can manipulate the other terms a lot easier if we do that. We'll show. We're going to transfer the signs of E and P from the phase to the operator. So before we had one operator and 4 phases, now we've got 1 phase and 4 operators. Okay, can you see that, what I've done there? I've got rid of any plus and minuses in the E to the minus term, they're all the same, and it's been transferred to the operator term on the left. And by the way, I don't use sigmas in any of this because we don't need them if we use multivariate vectors. So we've got the Feynman representation of negative energy states associated with negative time there. If you look at that, negative time, the opposite time, you get the opposite energy. And so with only a single phase, you get that expression. However, I'm going to make it a bit more convenient because I'm also going to multiply it by I, minus I, in fact, and get rid of some of that variation. So I'm now going to have minus K plus IP plus Jm. Right, so that can either be an operator because we're used to using E and P as operators, so they become d by dt and d by dx and so on. They're just operators, or they're parts of the eigenvalue, the wave function, energy and energy and momentum. So if that's a nilpotent, then we just stick that down and we get that equals 0. And it's convenient if we've got 4 terms to make the first a row vector and a row vector and the second a column vector. But we'll just imagine that that's the case instead of bothering to write it down. And of course, this is a perfect expression of Pauli exclusion. No two can be the same, because if we got two have got the same amplitude, then they're the same, and they can't be the same because they will zero each other. And now we can do the Dirac equation in a dead easy way. It's a dead easy equation to create. Now we take the Einstein relation without the C's, factorize, and then just change the first bracket into operators and stick the phase factor at the end. Very easy. And we don't even need to actually put the operators in. We can take E and P to be operators. So it's dead easy now. And we can also create the Klein-Gordon equation out of the same structure, because that's just two lots of that, the same operator. Now, this is an important point. Now, we've been fiddling with the free particle, but it's not unique to free fermions, Pauli exclusion. It's true for any fermion in any state at any time. And now we're going to make a big change. We're going to say all fermionic amplitudes in all states are nilpotent. And if it works, then it works. And if it doesn't, we throw it out. But we know that it does work, otherwise I wouldn't be telling you. We say the most general form of a wave function is nilpotent, and we should seek nilpotent solutions for everything. And if we get that, we got a zero condition, and that's always been the way to universality. Newton's third law, conservation of energy, Lagrangian operators, all that sort of. And now we don't need an equation at all. We've actually got rid of all the equations of quantum mechanics. We just need an operator. So if we got an operator of that form, it will completely determine the phase that determines the nilpotent amplitude. And I was mentioning rhyming slang the other night, and essentially you have one word, you have the thing that rhymes with it, and then you have you have the thing that goes with it, and then you have the thing that rhymes with it. So you have an operator, you stick a phase term on it, and you get an amplitude, and that's the amplitude is what you play with. So once an operator is defined, we only need one phase. Dead easy. Operator acts like a tuned antenna. So finding the solution is just finding that phase. So the operator's out there, and it finds the phase out there that it wants among all the stuff that's out there in the vacuum. So we can replace E and P, if we like, with covariant derivatives. We can add potentials to them, potential energy terms. Or we can add the curvature terms if we're that way inclined, which I'm not, but we could. Well, that expression will always apply, whether there's any terms added or not. The phase term now, if we make E d by dt plus E phi, then the phase term is no longer a simple exponential, it's something else. But we have to work out what it could be. And any particle with a nilpotent wave function is automatically exclusive. Pauli exclusive, and combination state in an identical particle is always zero. So let's try doing the other way we do Pauli exclusion: psi1, psi2 minus psi2, psi1, being antisymmetric. They're antisymmetric, so there'll be a difference between them. And what's the difference? Well, we work out the difference. Interestingly, it's minus 8i p2 cross p1, or 8i p1 cross p2. So immediately, yes, we've got Pauli exclusion the other way now, because we've got the difference between psi1, psi2, and psi2, psi1. So the result is clearly antisymmetric, but it tells us something new, because this is an important new aspect. Because if you look at that P1 cross P2, or P2 cross, that's all that's left. And the only thing that's stopping that cross product from being zero is actually the direction of the P1 and P2. Leave it till after. The only thing is that's stopping it from being zero is the direction, and which means that fermions are simply determined totally by their direction in spin space. They're not determined by anything else. Magnitude doesn't matter or anything else. It's just that direction that matters. All must have a different direction. we can imagine putting a plane on the vectors on the end of each vector, and all the planes would intersect. And that would create a Euclidean structure if we had an infinite number. So this is just pure formalism. We've done nothing except, you know, alter the formalism. It drives us towards an understanding of the universe that you can't separate the universe from the fermion. And now we start beginning to understand what we mean by vacuum. I suppose I have always been a believer in that everything is nothing altogether, fundamentally. That's the only way anything works, if you start from nothing. So suppose we want to create a fermion out of nothing. And we want it to have interaction potentials in it. We want a special fermion. We'll give it a wave function psi f. Then we're going to leave a hole in the creation that's left by that fermion, a hole in nothing, if you like. That can be described by minus psi f. And the superposition of the hole and the fermion is 0. It's just 0. So it's comprehensible only if the entire universe adds up to nothing. And vacuum is the hole in nothing left by the fermion. But of course, vacuum isn't nothing, because a hole in nothing isn't nothing. To create the fermionic state with all those interaction potentials, we've got to create the environment, which means that fermion can exist. So it's the whole environment of the fermion is what we mean by vacuum. And all its effects have to add up to minus psi f. So the vacuum for any fermionic state is the rest of the universe, which makes that state possible to exist. And it must be a mirror image of the fermion state when you add up everything together. So we can say that no two fermions share the same vacuum or the same phase. And now we can see what local and non-local mean. We've got an object like that. Everything inside the bracket is local. That's what local means. If it's inside that bracket, it's local. If it isn't, it's not local, non-local. And everything outside, superposition, combination, all that stuff, is non-local. But that doesn't mean they're not related. When you've got a fermion or a vacuum, you have to do both a local and a non-local description of it. So the non-local can cause local changes and vice versa. Local changes occur inside the brackets on the E and P terms. If you put something in E or P, it changes it, and that changes the local term. And that will change the vacuum which it interacts with. And the other way around can happen and will happen, as we will show. So you have to have local and non-local descriptions, because both particles and environments are equally involved, which of course is what makes calculation a lot easier, because you've got two lots of information. Now, locality is all about defining a fermion state in the first place. You're actually creating something localized, a point-like particle. And it's entirely specified by the Clifford algebra operators. E and P and M are irrelevant. They're just scalar factors. I mean, they're important scalars, but that's all they are. So the Clifford algebra is actually doing all the physics for us. We know that the Clifford algebra has intrinsic meaning, so we expect to find even more physical meaning in areas we haven't investigated. So let's do a dimensional analysis on the components that created that Clifford algebra. We got a complex number, we got a vector, we got a scale, and we got a quaternion. And we can identify mass is scalar, time is complex, and space is vector. So what is that quaternion? Not obvious, but there is an obvious candidate. If we extend dimensional analysis beyond classical dynamics, gravity, and that kind of thing, we end up with electromagnetism, in which something like charge is the thing that's missing. And we got three types of interaction like that, strong and weak, as well as electric. And we know that they're similar. And we know that under identical conditions, they would probably behave identically. And we know that identical charges produce opposite forces to what identical masses will produce. So our good bet is that charge is a quaternion. defined this way. And we will define I as strong, J as electric, and K as weak. And we'll show why later. But the symmetry between them is broken when we create the local fermionic state. That absolute equality is only true in a non-local way. It's not true in a local way. And when we break that symmetry, we've seen a quaternion take on vector characteristics, or the charge takes on vector characteristics. The other charge, electric charge, takes on scalar characteristics, and weak charge takes on pseudoscalar. And we'll soon see that it works in the interactions. And this goes back to something which is very old in my work, that if we do charge in this way, we will have a perfect symmetry between mass, time, charge, and space, which is a group of order 4, Klein 4 group. And we can represent it in hundreds of ways. I've got tetrahedral represented, cubical, colored circles, Venn diagrams, you name it. Just name me one and I'll probably do a representation. That's one representation. I got my friend Vanessa Hill to do that diagram for me. And I was saying these 3 properties here is what causes e to the I part pi, because the first property is essentially, that's e, yeah, because it's differentiation and integration, so it's conserved, non-conserved. The I, of course, is really imaginary, and the pi is the dimensional one, which is commutative, anti-commutative, which rise from 3-dimensionality. We got a table, Klein 4 group, and I'm saying TCP, I need to do it that way because I've got my parameters organized in that form. It's really MTCP, because that mass acts as an identity for the group, is derived from the larger time, charge, space group. You can see it's mass, time, charge, space, MTCP. And the same structure has been observed in cellular automata. When you get them universally Turing compatible, the 4 cellular automata that are universally compatible have analogs to TCP transformations. Mainzer did that work, and if I apply my ideas to that, I get Klein 4 as well. And this is another one you can get, identity in 3 double quaternions. There's also a Klein 4 group. It's called the H4 algebra. You could also use double vectors, but this time you have to use negative ones. I think this just pushes it forward, whatever you do. That's better then. So I'm saying quantization and relativity are automatic consequences of compressing the 8 original global units into a combined local structure, which is based on the generators of the group. How we're doing? Oh yeah, I've got plenty of time. The physical meaning is in the algebraic operators. The compression produces the new local composite quantities. And by the way, something that struck me when I was looking at Dirac equation for a long time, they kept going on about 4 vectors. Well, that I d by dt thing and I gamma d by dt, gamma naught and what is it, the gamma delta, gamma del, that they are not a 4 vector. They include a 4 vector, but they are not a pure 4 vector because they need different quaternions in front of them to make it work. This is a CPT symmetry, can be done, but using pre and post multiplication by I, K, and minus J and J. It's easy to show the results that come out of that. Now, if you look at why we got 4 terms in the spinner, the basic state of the Dirac equation, we got 4 terms because you got the lead term and the P, C, and T transformations of it. That's what it is. It's the identity P, T, and C, or C, P, and T. They're like vacuum reflections of the real particle state. And I did some argument at one time about how the mirror reflection was actually one of these vacuum reflections. Now, a fermion can't form a combination state with itself because that will zero immediately. but it can form a combination state with any of the vacuum reflections. And we would get boson-like objects like that. That's reflecting the E. Second one's reflecting the E and the P, and the third one's reflecting just the P, and those are TCP. And that will be a spin 1 boson, a spin 0 boson, or fermion-fermion combination, Bose-Einstein condensate, or Berry phase, or something like that. Now we can see immediately that spin 1 boson can't be massless, because if it was massless, what am I doing here? Yeah, that's right. Yeah, if we do that, we would get immediate cancellation. Spins, I'm sorry, I got it wrong. A spin 1 boson can be massless because we can write that first equation without zeroing. But you notice the second equation must zero if it's massless. You take the minus out and you've got the same term in the two brackets. So that one would zero. Spin 0 boson cannot be massless. So there's no Goldstone bosons, and Higgs must have mass. And no fermion can be massless, because if a fermion is reduced to the two terms, the E and the P, then you can't distinguish from other terms with the same ratio. So it can't be specified as unique. I'm just working out one of these using all 4 terms to show how you get a scalar multiple by doing the fermion, the boson. So we can define the entire structure of quantum mechanics by defining the creation operator for a single fermion as a nilpotent. And there are 4 creation operators, or 4 annihilation operators, or 2 of each, depending how you want to do it. And that's what it is. But only the first defines the real state, the other 3 are vacuum reflections. We can do it in another way. If we take the nilpotent object, IKE plus IP plus JM, and we pre-multiply by KI or J, then you get the IKE, etc., multiplied by scalar. And you can do it an infinite number of times. So these are idempotent terms. Idempotent means it multiplied by itself, you get itself. 1 is idempotent, 0 is nilpotent. So these partitions we can describe as strong electric and weak interactions, vacuum. So I can do, if I write that first equation down there, first expression, then it's just the same as just writing the first bracket, because everything else is idempotent. But I can also apply the 2 Ks either side of the second bracket and change the E term over. That will flip the E term over. And so what you're getting there is you're getting fermion and its vacuum reflections to infinity is the same as a bosonic state. So fermion is a boson in vacuum. It isn't in when we isolate it, but it is in vacuum. It's a boson as well as a fermion. So we can define an operator. Well, the equation is totally redundant in many ways, which we only need the Dirac operator. We don't need the equation. Get rid of it, because we've already got all the information we need. We give our state, and then what we do is we operate that as an operator on the phase factor. We get an amplitude and we square to 0, and we know what it is. I'm saying if you do a sum and a product of the nilpotent, you get another nilpotent. So we can see large scale systems made of nilpotents are going to be also nilpotents. That's a very interesting fact.
Did you say a fermion is a boson in vacuum?
Yeah, fermion is the same as a boson in vacuum, and that's important for calculations, as I'll show. This is about helicity. I'll not say too much about that. So this is, somebody quoted T.S. Eliot earlier. Quote T.S. Eliot again. Do I dare disturb the universe? This is a love song of J. Alfred Prufrock. So the phase factor is now simply an expression of all the possible variations in space and time which are encoded in the creation operator. That's what it means. It's uniquely defined once the operator is specified. And so a fermion is just a set of space and time variations. The mass term is purely passive. It's convenient, but it's not necessary. and we can actually show we don't actually need it. And we can't define an isolated system. There's no such thing. Once we define a fermion, we've disturbed the universe. Energy conservation only works over the whole range. That leads up to laws of thermodynamics, which we won't bother doing. And this is using discrete differentiation, something Lou Kaufman's interested in. You can replace differentials by commutators, and I've done that. And what I find is I don't need the mass term in the operator. You can see my operator there in the middle equation has no mass term, just the object, the differentials. And this you get nil potency. You get a mass term in the wave function, but you don't get it in the operator. Now, the reason why that's important is because normally you can't transfer from classical to quantum this way, but you can if you do it using a nilpotent, because you can multiply or the whole thing on the left by IH bar, and you will get the quantum version, and that's just multiplying it by a scalar. But if you've got a mass term there, you can't do it because the mass term doesn't have an I compared to the other two. So you can do a smooth transition in that version of quantum mechanics. I'm saying something about mass there, but I'm going to leave it. I'm saying that mass isn't, of course, a rest term, as we know from Schrodinger's solution of the Dirac equation. We get Zeta-Bewegung, and that means that even so-called rest mass is motion, mass of motion. And let me show you, I got shouted at by all the idempotent people, some of whom used to be here at this meeting, because I said it's nilpotent. It can't be nilpotent. It isn't. It's idempotent. And there we are. You see those two equations? What's the difference? The only difference is that one small operator is on one side of the bracket in one, and it's on the other side in the other. It's the same equation. It's just differently organized. It's the same information. And they've missed out on the nilpotent because of that.
Associative law.
Yeah. Thank you for that. So it doesn't make any difference in the physics or mathematics, but you learn more from the nilpotent version. And it must have been a nilpotent from the first, because you multiply it from the left. So whatever it was, and if you multiply it from something, it's not going to change fundamentally. And the nilpotent version is fantastic for calculation in a way that the idempotent isn't. But there's an extra constraint, which means that every fermion holistically and non-locally connects with the rest of the universe. And we get rid of a lot of the apparatus of quantum mechanics and quantum field theory. It's total garbage. Now, this is very significant, and I'm not going to do all this, but this is very significant to my argument. My argument is that everything's coming from those two terms that Dirac added for convenience. And so far it has. What I'm now going to say is that there are only 3 Dirac solutions for a point-like fundamental particle. Nobody's ever done this before. They've only found one of them. They've not found all 3. And it doesn't work if you've not got a nilpotent wave function. And this is why those two terms added to the Dirac equation actually introduce nearly all the standard model in one form or another. And I'm going to outline what I'm going to do, but I'm not going to go through these calculations because they're too extensive. First one is the Coulomb interaction, the so-called hydrogen atom. And there I've actually used Dirac's conversion to polar coordinates. And you see that the del term has been changed to a bracket with d by dr and other terms in it. That's what Dirac did. If I look at that and then say it's got to have a nilpotent solution, well, it can't have. There's no way it can actually zero unless E has a 1 over R term in. 1 over R term is a Coulomb potential. So simply from spherical symmetry, you've got a Coulomb term for every one of these interactions, just by spherical symmetry and nilpotency. So the K must have a 1 over R term like that. Once I put that in, then it's a doddle. Can do it in 6 lines. There we are. That's the whole solution in 6 lines. But I'm not going to go through it today. Now that's okay, but that's been done before. But even if it took 60 pages, it's still a solution. But I've got it in 6 lines. But I'm saying that there are only 2 other solutions which work for nilpotency. And one of them is Coulomb. It's always got to have Coulomb because of spherical symmetry, and a linear potential proportional to R. And the other one is Coulomb term plus any other potential. The first one gives you the characteristics of the strong interaction. The second one gives you the characteristics of the weak interaction, the harmonic oscillator. Let's look at the strong interaction briefly. Now we got this quark model. What I'm saying that all that we're doing there is putting the combination state of 3 nilpotents. But of course we can't do that because it's 0. But we can do it if we separate out X, Y, and Z. Now we can do it. Now I multiply those out and say, let's suppose that we make X, the PX got a value, and PY and PZ 0. Then what we'll end up with is if you see below the halfway down, you see the first equation there. On the right, you see what it turns out to be multiplied by a scalar, which we'll remove. If we put it in the middle, it'll look very similar, except that the P sign is flipped. It'll flip over. And if you do it at the end, it'll look like the first one, but the PX, PY, PZ. So just by putting those in, we will get something that looks like one of those nilpotents. But we've got to be able to flip the I. So we've got to have equal numbers of plus and minuses to start with. Plus and minus P's, same E, mass. The proton must have mass. Anything like that must have mass. Otherwise, you can't do it. And what kind of mass is it? It's a Higgs mechanism mass. It's not something peculiar. It's not something, oh, it's due to the colored gluons doing this, that. It's due to the colored gluons, but it is actually a Higgs mechanism mass. You've heard many people say 98% of the mass of the proton does not come from the Higgs mechanism. Rubbish. All of it does. It's just in a different form. And your mediators look like that, and then there are 8 of them because through group theory it reduces to 8 instead of 9. The phases, see those phases look exactly like the combinations that I've just done. They're the same structure, and that solves many problems. And by the way, the first one, if anybody wants to nominate me for the Clay Institute Prize, it's worth quite a lot of money. And it would be very useful to AMPA, to have that money. If anybody wants to, nominate me, there you are. One of the Clay prizes is to prove why the proton must have a mass. They're fumbling around with all kinds of nonsense, but it's simple. So that's the strong interaction. And then what I do is then say that if we take those three objects there and rotate them, which is what you're doing by changing which one's 0, then what you're getting is a fixed force. You're getting a fixed rate of change of momentum. A fixed force is a linear potential. So that interaction alone is a linear potential. Then all we've got to do is put it into our equation. Now you see the potential equation as A over R plus BR, a different term from the last one. And we can do a phase term for that. That's the thing that we have to be able to do. And then we just work that out and we get all this stuff. And eventually we can show that it's got exactly the same characteristics as we expect from the strong interaction. So finally, we get to the weak interaction. What do we do for that? Well, we say, basically, weak interaction is creation and annihilation. Creation and annihilation is boson, fermion, boson, fermion. The weak interaction, and even that oscillation between the 4 terms in the Dirac equation, the Zitterbewegung, is a weak interaction of that kind. And the reason why it does that is because the E has an I on it, and it's plus and minus. And let's just say we know that's clearly a harmonic oscillator of some sort, but we don't have to guess what the form of it is. It's clearly not linear because that's the strong interaction. It's clearly not Coulomb because that's all the interactions. It's just something else. Let's say CR to the n. And if we solve this using our methods, only works for nilpotents, we find we get harmonic oscillator for anything, for any n. And we know that it's probably an inverse cube or something, but it doesn't matter what it is. If any combination, in other words, will give you a harmonic oscillator. It's because you're combining different ones that you get. And that's what the weak interaction is all about, combining different ones. Yeah, I'm not going to do the details of that because that's quite involved. But you get a harmonic oscillator. So we see the nilpotent structure with its pseudoscalar, vector, and scalar already incorporates the fundamental interactions. This is half of the standard model is the fundamental interactions. And I'm explaining where they come from and how they fit in. I'm not going to go into the details again. Quantum field theory, the easy transformation, because we're already using annihilation and creation, already using that. We don't need a dagger and a, we don't need all that because we've already got annihilation and creation in it. Supersymmetry renormalization. Well, in fact, we can show that that we don't have an infrared divergence and we don't have an ultraviolet divergence. The two things that screw up quantum field theory. I do a perturbation calculation here using a nilpotent and find that essentially it comes down to the fact that we've got as many bosons as fermions, because a fermion is a boson is a fermion in vacuum, and it's vacuum that we're talking about. And in fact, it eventually comes down to arithmetic, and I love any calculation that just ends up as arithmetic. You see, you've got very simple arithmetic there, which cancels everything to zero. Very, very simple. Love it. Look at that. Beautiful arithmetic. -2 + 3 + 0 - 1. I've got rid of the divergences. And the other one is the infrared divergence, which comes from the propagator. And the way that Feynman and other people did propagators, you got something like that. Yeah, essentially that's something looking like that. That's a fermion propagator. In other words, it's the inverse of the amplitude in effect. Now, the particle is its own singularity in these. I'm not going to go into detail. But I say that way of doing propagators, if you do a boson propagator, what they try to do is have a Klein-Gordon propagator. Now, they always talk about Klein-Gordon being the equation for bosons. That's total nonsense. The Klein-Gordon is a general equation of conservation of energy, true for fermions as much as bosons. It's not a particularly boson propagator thing. So they create this Klein-Gordon propagator in order that it won't zero, because if you do the three terms in the Klein-Gordon and square them to themselves, it'll be zero. So they always change the sign of the M. Now, if we do it in terms of what we really have, spin 1, spin 0, paired fermions, we'll get something looking like that. And we find that that will never go to zero. In the nilpotent version, only squaring with itself goes to zero. If you multiply by any complex conjugate or anything like that, it's never zero. And the reason why the infrared propagators goes to zero is an artifact of their mathematics. It's not true. It's not a true bit of physics. They force you to have a pole where it goes through zero, but it never goes through zero with this. So that's enough of that. But I've done the full details for the final paper. Now, I want to say something about the significance of multiple pentads. Why have we got so many of these? Well, we've got a lot of particles, haven't we? So if you've got one state, then you're thinking there must be many simultaneous other types of states which could exist with the others. And if you look at these, you've got something that looks like the six fermion states. And that one is the quark states, because I've got an or between the first two terms and second and third term. If you then say another way of doing it is to say that it's a transition. The transition is caused by one term. So you go to the next generation, or you go across the generations from the up state to the down state or something. And it's an algebraic transformation. And those are the possible algebraic transformations. Out of the 64 units, they all have to have a quaternion in. And the only ones with quaternions in are 48, and those are the 48 with quaternions in. And those are the transformations that you can do. And the other 16 are just space with no quaternion in it, where you've got no particle transition at all. So I'm going to summarize now. Dirac set out to produce a relativistic equation for the fermion. So a fantastic piece of work, but it took an enormous guess, and he decided he needed to square root a quadratic equation, basically something like the Klein-Gordon equation. And he wanted a linear equation. You can do it using anti-commuting operators taken from abstract mathematics, and Dirac chose to use 4x4 matrices. As I say, it's only one formulation. And even with the matrices, there's no unique formulation. It turns out that these operators, and every subsequent model of them, are components of a group with 64 elements and 5 generators, a double space creating zero totality. Ultimately, this is all we need to construct all physics. I mean, I'm a long way into it, but there's still a bit of work to do. You've got to get the masses of the particles and stuff. The operators actually used in the equation and those that could be used have different functions, and they lead to interactions of the standard model and the broken symmetry. So there's two different types of operator. There's those that lead to the standard model with the broken symmetry, and those that lead to the particles within the standard model. This algebra was forced on us by mathematical requirements so we could make the equation linear. But we got a fantastic result out of it. It's got the potential to explain a huge amount of physical structure. The equation's nearly 100 years old, and it's taken us all this time to get anywhere with that. We just use these as mathematical objects, but they're not. I found it relevant in other areas, and biology was mentioned this morning, and I found it relevant in the genetic code, which has 64 elements, and with Vanessa Hill, we worked out the genetic code using it. And in any context where two spaces are relevant, Mike Horner talked about two spaces this morning. Anywhere two spaces are relevant, this is important. And that's virtually anywhere, because you've got appearance and reality and all that sort of thing. Object and environment is another one, and John Torday in the cell. And object and environment is a universal condition, and I worked with Peter Marser a lot on that, and we did a lot of stuff on large scale systems. And also, because of E squared minus P squared minus M squared is the true equation, the nilpotency is true wherever we got conservation of energy or anything remotely resembling it. So ultimately, Dirac's alpha and beta, they introduced something with a convenient fix, and that's still largely treated that way, have essentially ended up by opening up the world of fundamental physics and a great deal more besides. Okay, thank you. Sorry, I have to be so quick.
The EPNM states, if they are equal,
Equal to what?
if E1 P1 N1 equals E2,
Okay.
yeah, like that, of two fermions, does that mean that their direction planes have the same angle and are equal?
Yeah.
Therefore, two fermions annihilate each other.
Yeah.
Does that mean that the vacuum state is all the fermions equal EPNM states, or all fermions?
All the potential vacuum has got all the potential fermion states, but we never observe it or anything like it. But they only work if they're equal. Yeah.
So the vacuum can be seen as like all the fermion states with equal EPNMs.
No, all the fermion states with any EPNM.
In EPNs.
Yeah, but different from the one you've got, which is your particle, which you've localized.
Right. And the other question I had was, is the ratio E to P equal to the angle of the fermions?
Depends what the angle's measured against, but in principle, it is. Yeah.
And one last question: how are local and non-local related to quantum entanglement?
Well, non-local entanglement's non-local. Okay. Anything non-local is entanglement.
Yeah, I'm curious about saying the gamma matrices are parts of a 64-dimensional algebra. If you multiply the gamma matrices together, you get 16 matrices that are closed. So I always took the opinion that they're part of a 16-dimensional Clifford.
Oh, there is a 16-dimensional within them. But if you try multiplying them all out, you'll find 64. If we go back to that table.
I've done it, and I got 16.
Oh, well, have another look at it, because I think you'll find there's a total of 64. Oh, yes, it does include, depend on whether you include gamma.
Oh, it's 16
Gamma
with 16 without gamma 0.
Yeah.
Yeah.
Gamma 5.
Yeah, gamma 5.
Yeah, that's what I'm saying. The 5 give you 64. 16 is from 4 of them. That's correct. But I use gamma 5 or I. You can use I instead. And Sydney and I did all the possible potential versions of this.
My memory's a little weak on this. We think all that gamma 5 is just all 4 gamma matrices multiplied together.
That's correct. Well, and I, and then gamma 0, gamma 1, gamma 2, gamma 3. But it's another way of including I in it. It's another way to, if you complexify it. It's another way of complexifying.
Okay. Right.
It's an alternative. So, how are we for time?
Can we still ask a question?
Yeah, I need to start the next presentation.
Albert Giesen is a question.
Yeah. Oh,
Yeah.
Albert, yeah.
No? So
No.
it's and
Yeah.
There's no-
Oh.
I can't see. Can you? No, you can leave the recording on for the questions. Albert?
yeah, okay. All what you have explained us here is a very sophisticated way to describe the physical world. But I think the goal should be to understand the physics which causes this formalism.
That's what I'm
And
doing.
that is what I find missing. For instance, one example, I could see you in a lot of things. Why comes inertia from? I've once explained how it can be explained. Higgs is not a good way. It's a better ways. Another thing you have here mentioned is the Pauli exclusion. Pauli exclusion is a rule we know how this rule is, but there is physics. There's a physical process behind this principle. The goal should be, I think, in physics to understand the physical process which causes the Pauli exclusion to be valid.
I have explained it via physics. That's what that dual group was. Nothing could be more physical than saying space and another space. That's extremely physical. And if you look at that group, I've always explained it via physics.
Oh, I doubt that space has something to do with physics. Space is not physics. Space is a structural idea.
Oh, well, if you don't think space is physics, then we're not on the same common ground with discussion. Because
Yeah,
I think
okay.
space is physics and two
Okay.
spaces is physics, in my opinion.
But is that what philosopher the philosopher Plato has understood to be physics, but we have now a different understanding. Also, time is not physics, but it's structure. But okay, maybe so you are too different. We cannot discuss it here.
No, we can't discuss that if we don't have any common ground on that.
Yeah, okay.
So we'll leave that one for the moment. Should we switch off the recording soon?
Yeah, I'd like to ask, what is physics? If space and time isn't in physics, what is physics?
But it's a question to me. Physics is charges and forces. That is, for instance, physics. These things which Newton has done to build, for instance, a planetary system. Plato has said if planetary system is because a circuit is a fundamental structure in our world, so everything has to fulfill this structural requirement. And Newton has started another way to say we have forces and masses, and that is physics, and we have lost it in the recent years, I think.
Well,
Okay,
you can
that's a
do
more fundamental
Newtonian physics with what I'm doing, because Sydney's done some, haven't you?
Mhm.
Done Newtonian physics with these nilpotents. You know,
Yeah.
simple Newtonian questions you can do with nilpotents.
Maybe there's a good formalism to describe it, but that is not the physics behind it. It's a
Well, I'm
process.
sorry, if you don't think space is physics and time, and then we're not on the common ground.
Well, yeah,
I
and Newton's laws are within space and time. That
Space and time is a structure. We have built it as a good structure. We have built it with our minds to build physics in it. But the fundamental ideas of physics, okay, maybe it's too far away, but that is not.
Well, I think these
forces
are the
physics and
fundamental
charges
ideas of
are
physics. But
Okay,
yeah.
okay,
yeah, we can't discuss it if we're not on that common ground.
okay, yeah. But it's not my idea alone. It's a long discussion what space and time is, especially time. There was has been a lot of